So a big thank you to the team for organizing this amazing conference. So I will be telling you a little bit about what we do at Mossy Earth and then try to explain why testing conservation actions really matters to us, and then give some concrete examples of how we are starting to carry out some small tests at our rewilding hubs and also through our dedicated innovation program, and finish with some simple recommendations that people can use to sort of design more effective tests. So Mossy Earth is essentially a membership to restore nature. We have people who support us, who make monthly contributions, and we use those funds to carry out the most cost-effective interventions we can around the world. And then we, regardless of the outcome, we share the results through our YouTube channel and through different platforms so people can judge us and we can build that trust and grow support. And one area that we're focusing on at the moment is to develop these teams in these 4 locations that are trying to think at the landscape scale and deliver impact for the long term. We're also working with partners, organizations as funders, and we're focusing on actions that we think are particularly high leverage, where small interventions can have large-scale impacts, or where the cost of inaction would be very large and irreversible. And since last year, we kicked off our Rewilding Innovation Program, which focuses on funding through small grants, tests, and trials of novel ecological restoration methods. So looking at the little matrix that Bill presented, what we find is that we can very often be in this situation where the evidence base is weak for a specific action that we're trying to implement, because the evidence base is thin in conservation. But the issue is that if, when we're planning our projects, we find that we also haven't designed it in such a way that we will be able to learn from it, then we can just be in this guessing trap. And the reason we think testing really matters is essentially that it's a way to get out of this trap. So if we design an effective test, then we can start moving into a stage where we can start refining things, and eventually we can be in that sort of just doing phase and implementing actions confidently. So to make this all a little bit more concrete, I'll give some examples. We are working with our local teams to come up with which areas does it really make sense to be carrying out tests, and we've narrowed down that it really makes sense to focus on the things that we're going to be repeating often, that are larger scale, and that we're going to be focusing on for the next few years. So looking at with our team in Indonesia, the situation there is that we have these large areas that have been damaged by dynamite fishing, which leave these huge rubble fields that are sort of stuck in a degraded state. And the solution we're implementing there is to stabilize the rubble with these sort of modular metal structures. We collect naturally occurring coral fragments from around the area, and we attach them to these structures. This is just to show you what this looks like in practice. So this is one of those rubble fields. And 1 year later, after the structures are in place and the coral has attached, you start seeing that it looks like this. But there's some important caveats. And one of them is that the attachment process we're using is actually using these plastic zip ties. And the coral ends up growing around the plastic, but it is plastic that ends up staying in the ocean. So it's something that we wanted to avoid. So we decided to just run a small trial looking at different materials that we could use for this. We have hemp rope, cotton twine, aluminium, and iron wire as locally available materials that we wanted to test. And the neat thing here is that we could, each of these modular structures could serve as a small test because we could have all the materials in each structure. Interestingly, all of them were sufficiently stable for the coral to attach in some cases, but we noticed huge differences in the probability of attachment. And the only material that seemed to emerge as a good alternative would be this aluminium wire. And so based on this, we are now in the current deployments using aluminium. Moving on to the Ecuadorian Amazon, we have the situation where we're working in an area where roads create a barrier to canopy connectivity. And this is especially troublesome for arboreal mammals like this sloth that we found struggling to cross the road in this area that we're protecting. So the solution here is to implement these rope bridges that just allow them to cross it. This is something that's been done in many places around the world with interesting results. And so far we've seen these 4 species using them already. But because we want to do this at scale, we thought it would be an interesting opportunity to look at different designs. So we created this this experiment where we have paired bridges, where one rope is just a simple nylon rope, the other one is reinforced with a steel cable so it's more stable. And we've also set them up so that we're testing the effect of having a bit of an artificial canopy over the rope bridges to see if that makes them more usable or more interesting for the animals to use. And finally, in Portugal, we have this situation where we're working with an intervention that has the potential to have a huge scale, which is to cut down eucalyptus in abandoned plantations to allow the natural regeneration of native oak forests. But the challenge we have is that after you cut the eucalyptus, it resprouts vigorously, and we need to still do some work to kill the stump. And in sensitive areas like next to a river where you can't apply herbicide, we do this by repeatedly cutting those resprouts. But there's no real recommendations on what the most effective frequency is. So we're just carrying out a simple trial where we're testing different frequencies to allow us to see which one ends up killing the stump faster and at the lower cost. And we expect that because we are going to be doing this repeatedly, we could save really a lot of time and money by doing this. And the other way we're supporting tests is through our dedicated innovation program, where we set aside in this first grant cycle 60,000 pounds to be allocated in small grants. And we received about 40 applications in this first cycle, and we ended up selecting these 6. And they range from things that are like testing the use of ants to assist the ecological restoration of degraded drylands, to comparing different seagrass restoration methods in Tanzania, or even looking at ways of using microfiltration to improve freshwater quality here in England. And it was great to see we had applications from all kinds of places around the world, and just reviewing these applications, because each of them had an experimental design, provided us with an interesting window to the kind of trials that people are designing. And I want to tell you a few things that we noticed from evaluating those designs. So here you can see the number of replicates per treatment in those trials, and this is something that's already we've been discussing, which is that they tend to be small. And especially, if we put this in the context of the medical literature, most of these would be classified as pilot or very early stage research trials. But that doesn't mean they're not valuable, and many of them I think we can learn a lot from. And a positive takeaway for me is that there is actually a lot of things that we can test with a moderate budget and a timeline of 2 years, which is the scope of our grant. So I think there's a lot we can do. And so when we think about this issue of having these small sample sizes, I think the other thing we need to consider is that often, we have a small power, and power analysis is not something that's often done. And often when people explain how they're planning to analyze their experiments, they're looking at the sort of null hypothesis testing approach. And all of this sort of puts us at the risk of having lots of small trials that have a low statistical power, and that we will end up having a lot of things that are deemed as non-significant, and that this is misinterpreted as the interventions having no effect. So this is a bit of a danger that I'm sort of noticing as we see the kinds of experiments that people are designing. So I think it would be really interesting if, as a field, we can all sort of really move in these tests towards more focusing on effect size estimation. And where appropriate and interesting, we could try and start using other approaches like Bayesian methods. I think this is something that's having more traction in other fields and could be quite exciting. I think it could help us handle the issue of small sample sizes, of integrating multiple sources of evidence, such as local knowledge. And also it provides outputs that can be quite interesting for decision makers and intuitive for stakeholders to understand. So I'm excited to see what we can do on this front. Another issue that we noticed in these designs is that with these small sample sizes, and given that it's quite common that in conservation we're implementing actions in space that's very patchy and variable in terms of environmental variables and confounders, that we can end up in a situation quite easily where we have unbalanced experimental designs. So if you allocate your experimental units randomly in space, you could just end up with a situation where one group is more exposed to a certain condition than the other, and which could skew your results. So just a simple recommendation here is if you are doing tests with these sort of smaller number of replicates, you could try and use, for example, paired designs or randomized block designs. And if anyone's interested to discuss this later, I think it would be interesting to see how this can apply to different things that people are doing. And finally, we still see quite a few trials where we have this issue of pseudo-replication, where people are, for example, asking a question at the forest level, but the way they're designing their experiment and analyzing it, they're actually using the data at the tree level. So this can lead to overconfidence in the reliability of test results. And so the recommendation here is to really define experimental units that sort of match the scale of the research question that you're asking. So to wrap up, the three recommendations here for effective test design would be to move towards effect size estimation and Bayesian methods where appropriate, to think carefully about the spatial arrangement of experimental units, and to define experimental units that match the scale of the research questions. And so with all of this, I really hope that we can all test more, test better, and stop guessing so much.